Okay, good morning, everyone. Today we're going to start a new topic that involves real numbers. So up until now, we've more or less dealt with integer properties. And that's the realm of number theory and also the realm of something like maybe a modern intro to modern algebra course. Today we're going to start the other important topic or field for an undergraduate math major, namely real analysis. One of the most important topics of your undergraduate degree, especially if you're going to grad school. So real analysis is a must-have prerequisite for going to graduate school in mathematics. So let's start off with a theorem. So let's say maybe, so if A is a real number with 0 less than or equal to A, which is less than epsilon, for all epsilon greater than 0, then A is equal to 0. Okay? So this is a statement, and let's think about how we prove this. Does anyone have any guess as to how we prove this? And again, there's only 3 of you here, 4 of you here. So speak up if you can. Any guess as to how you prove this? So one aspect about real analysis that's going to help you is maybe if you draw a real number line. So here's 0, here's 1. And epsilon in mathematics, as I've mentioned maybe before, represents typically some small positive number. So maybe we should look at this by way of contradiction. So suppose that A is like right here, right? But then if A is right there, right, there's some positive quantity between 0 and A, right? And the hypothesis of this theorem says that A is strictly less than epsilon for all epsilon greater than 0, right? So couldn't we pick an epsilon right there? And then, oh, wait a minute, that would break the hypothesis. So maybe A doesn't exist right there. What if A is right here? Well, if A is right there, then maybe we can take like 1/3 of epsilon and call this like maybe epsilon naught. That's still a positive number greater than 0. So that would break the hypothesis here. Okay, so what if A was over here instead? Well, then you could just take this and say maybe like 1/3 of epsilon 0 and call it like epsilon 1 or something. And then you would be on the left-hand side of A. So what's happening here is that anytime we put A to the right of 0, we can always squeeze an epsilon to the left of it. It's still to the right of 0. So what this is telling us is if we keep on doing that, eventually it must be the case that a is equal to 0, right? So this picture is kind of helping us get an intuition as to why this theorem might be true. And with many proofs and analysis, drawing a picture is going to help. So the way that I would do this is I would do by contradiction. So this is like my sketch over here. So I scratch there. I'd say maybe by contradiction. And this is where having a solid foundation of the logic that we've been dealing with all semester comes in handy, because what does it mean to assume by contradiction? We assume the hypothesis, right? So we assume that a is a real number and 0 is less than or equal to a, which is less than epsilon. And a is not equal to 0. And this is again for all epsilon greater than 0. Okay? So what can we do here? So this is, we're assuming the negation of the hypothesis together, I mean of the conclusion together with the hypothesis. So how can this help us? Well, since a is not equal to 0, right? This implies that 0 is less than, strictly less than a. We know that it's greater than or equal to 0, but this, assuming the negation of this right here, says that it must be strictly greater than 0, right? So then, what we could say is then, if we just say something like, take epsilon equal to 1/2 of a, right? And since a is positive, if we divide it by 2, then that's also positive. So then 0 is less than epsilon, which is equal to 1/2 of a, which is strictly less than a. And this is a contradiction, because then the contradiction says it comes from the fact that this right here is being broken. If a is positive, strictly positive, right? Then if we set epsilon equal to 1/2 of a, that's also positive, and that's a positive number, strictly less than a, but this has to be less than epsilon for every epsilon. So this is the contradiction. So the way that this proof would work would be something like, by way of contradiction, assume a is a real number, 0 is less than or equal to a, which is less than epsilon, for all epsilon greater than 0, and a is not equal to 0. Okay? Then it must be the case that 0 is strictly less than a. Okay? Because it's a is greater than or equal to, but a, we assume that a is not equal to 0, so this is the implication. So then, or maybe like next, let epsilon equal 1/2 of A. You can say something like since 0 is strictly less than A, we have 0, which is strictly less than epsilon, and epsilon is equal to 1/2 of A, which is strictly less than a contradiction. Okay. So what this theorem implies, right? This implies that there is no smallest strictly positive real number. Okay. There's no smallest strictly positive real number. Okay. Because if you assume there is one, then you can always take like half of that. You get a smaller one that's still greater than 0. All right, so 1 to 10, this is your first real analysis proof. 1 to 10, 10 being hard, 1 being easy. What level of difficulty is this theorem?
I kind of felt like it was a little tough, I guess because I didn't really know where to start here.
Right. And
But
that's understandable.
okay. So I think I guess I just have to practice more
Yeah,
because this is a neat topic, right?
right, right.
Okay, so I think maybe that's why. But at least in my opinion, I felt it was a little harder than what I'm used to seeing.
Okay, good. So that is a natural reaction to your first real analysis type proof.
Okay.
So I want you to pay attention though. In the way that I like to think of real analysis at the undergraduate level is you're really learning a collection of techniques, right? So before you see these techniques, they're going to be kind of difficult. But here, notice that I drew a picture first,
Mhm.
trying to like understand the theorem. And then I'm like picking a epsilon. It's like some ratio of A, the thing in question up here. And I'm also proving by contradiction. Okay. Um, and then also we have these inequalities everywhere and understanding that if both of these numbers are strictly positive, then if you multiply them together, they're strictly positive. And it's like, I'm like squeezing a small quantity greater than 0 between 0 and A. So I'm trying to find a way of looking at this number here and finding something in between there and 0, which is breaking this condition in the hypothesis. Okay?
Mhm.
So, okay. Um, that's one technique that is going to pop up quite a bit. It's like picking an epsilon in relation to some quantity that you're looking at. Okay? Okay, so let's look at maybe another one. Another thing that pops up quite a bit in real analysis. And that's looking at absolute values. So this is the definition first. So the absolute value of the number a, real number a, is equal to a piecewise function. So it's a if a is greater than 0, 0 if a is equal to 0, and negative a if a is less than 0. Okay. So just to make sure that you understand this definition, for example, like the absolute value of -8, right? Well, -8, the inside is less than 0, so this would be equal to negative of the a. So negative of -8, which would be equal to 8. In the next lecture, we're going to take a step back and build up the algebraic properties of the real number line. In this lecture, I'm just going to show you like little pieces of what we'll be doing from now until the end of the semester. So we'll build up why this is the case on Thursday. But just for now, a negative times negative is a positive, and this is the definition of the absolute value. So one of the most important theorems in analysis is called the triangle inequality. Okay, and it states that if a and b are real numbers, then the absolute value of a plus b is at most the absolute value of a plus the absolute value of b. And when you take analysis, you will not ever forget that inequality again. It's one of the most used inequalities that you'll see. So how can we prove it? I'm thinking we can just prove it directly by using the definition. So I'll say something real fast about this definition. This implies that negative absolute value of a is less than or equal to a, which is less than or equal to the absolute value of a. So this definition implies that this is the case. Right? So, for example, if a were negative, right? If a were negative, that's going to be positive, and then it's going to negative multiply that, so it would be negative less than or equal to that, which is less than or equal to the negative a. This is not hard to verify once you have this definition. And so, by the way, does this make sense based off of this? I can stop and explain it more.
It makes sense.
Right? Okay. All right. So I'll move on from it. All right, so let's look at the proof. So note, negative absolute value of a is less than or equal to a, which is less than or equal to absolute value of a. And negative absolute value of b is less than or equal to b, which is less than or equal to the absolute value of b. Okay. And again, this is, it might seem like, this is very difficult, and it's all coming out of nowhere. But this is just another tool in your tool bag of analysis things. Okay? So once we have these here, what we can do is say, well, then if we add these inequalities together, we get that negative absolute value of A plus, so it's like we're adding each side here. So minus absolute value of B is less than or equal to A plus B, which is less than or equal to absolute value of A plus the absolute value of B. Now, is that clear? Like, if I'm writing it here. And if you just add these inequalities together, that plus that is less than or equal to that plus that, which is less than or equal to that plus that. That's that line right there. Does that make sense? Maybe?
That makes sense.
Okay. So it just make it a little more concise, so it makes sense to do this. Right? I think that you see that that's the same thing.
Yeah.
Okay. All right. So maybe further. We know that negative absolute value of A plus B is less than or equal to A plus B, which is less than or equal to the absolute value of A plus B. Again, just like up there, the same thing, right? Actually, all of you have this written down, right? Like this definition. And you have that written down too, hopefully, right? Anybody?
Yes.
Okay. So maybe instead of writing it out formally, let's see how we could play around with inequalities to try to get that. All right, so hopefully you have that. Hopefully you have that. Okay. So imagine we don't know what we're doing, and we just want to somehow show this is what makes it so hard to teach via Zoom, because I can't literally see your faces and see what's going on over there. But I sensed that that was a little too much at first. So we want to know if this is true, and what are our tools. We know that absolute value of A is less than or equal to A, less than or equal to absolute value of A. We know that. Okay. So this is going to be a big board of scratch work right now. Okay, so suppose I didn't know what was going on, and I want to somehow get to this inequality. Maybe if I just look at that and I say, well, I know that negative absolute value of A plus B is less than or equal to A plus B, which is less than or equal to the absolute value of A I know that at least, right? And that sort of looks like this inequality, right? Sort of, right? So, okay. And then what else do I know? I also know that I know this. I know this. Okay. I know these things, right? So, maybe I can combine these two to kind of look like this piece up here, and I get as before. And then here. So I have all these inequalities. I'm trying to figure out how to like string them together somehow. Okay. But I know that I see that this and this, they look the most like what I'm trying to show. Right? So, okay. What are the two cases for a plus b, right? So notice, or note maybe, a plus b is either greater than or equal to 0, or a plus b is less than 0, right? One of these two things is true. Exactly one of them, right? Come on, guys, I need your help. Like, this is either positive or negative. That's what this is saying, right? Anybody? Are y'all with me?
Oh, yeah, I see it. Yeah, it's either positive or negative.
Right? So maybe we can consider this one here like case 1, and this right here is case 2. And just, we're breaking it up, so this is case 2, by the way, right there. So what we're doing is like, we're using what we know, right? This here, together with that there. And then that. And then we have these two cases, and we're just going to try to look at them and see if we can somehow test these to make sure that in either one of those cases that holds. Okay? So if a plus b is positive, right? Then what do we know about the absolute value of a plus b? What is it equal? Based off of the definition. And I'll write down the definition again because I'm not sure. So yeah, this definition is equal to a plus b if a plus b is greater than or equal to 0. I'm just making it more concise instead of having 3 plus and have 2. And negative a plus b if a plus b is less than 0, right? That's the definition of the absolute value in a concise form. So if it's greater than or equal to 0, then the absolute value is equal to that, right? Right?
Yes.
Yes.
Okay. Look right here. That's a plus b, right? So then this part right here implies that the absolute value of a plus b, which is equal to a plus b, which is less than or equal to a, with the absolute value b. Right? This right here, together with this right here, both of these imply this. And that's what we want. A plus b, the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. Do y'all see that?
Yes.
Right, because that, in this case, case 1, if that's greater, if the sum is greater than equal to 0, this is equal to that, which is less than or equal to that, which is what we want. Okay, so we know it's true if the quantity is positive. So what about if it's negative? And if it's strictly negative? Then, according to that definition, this is equal to negative of a plus b, right? Y'all see that?
Yes.
That's just the definition. Okay, we need to use the information that we know. So what do we know? Okay, this is equal to negative absolute value, I mean, negative a minus b. I don't know if that's going to help us at all. Oh, that is going to help us. Look right here. Multiply both sides of, so let me just rewrite this a little bit more formally here. So negative right there. Right there. We know that, so I'm going to rewrite this. So right here, a plus b is greater than or equal to negative of the sum. Okay? I see a negative a plus b right there, right? So if I multiply this by a negative number, this inequality flips. And I get negative times a negative, which is positive. So then I see that, oh, I have this information here. Negative of a plus b is less than or equal to absolute value of a plus the absolute value of b. So that is less than or equal to the absolute value of a plus the absolute value of b. In both cases, if it's greater than or equal to 0, or if the sum is less than 0, in both cases, the absolute value of the sum is less than or equal to the sum of the absolute value. Now, this is probably infuriating to you, honestly, because this isn't like the proofs we've done before. This involves a bunch of inequalities. And I think that that aspect is one of the reasons why um, students tend to struggle with real analysis when they first get there, because they're not used to dealing with inequalities. But realistically, all of advanced mathematics is done in terms of inequalities. A lot of advanced mathematics is done in terms of inequalities. Many of the things that you're looking at estimates where there's no way that you could possibly have an equation. So the best you can do is make an estimate in terms of some inequality. So that's a new aspect for all of you. So this is like our scratch work. All of this is like our scratch work. So let's see if we can piece this together in a nice package now. Okay. So I'm going to have to erase that. Yeah, I'm not going to have enough room. Okay, let's look at the. So we say let A and B be real numbers. So used to dealing with integers. Let these be real numbers. Okay. And observe that negative absolute value of A is less than or equal to A, which is less than or equal to absolute value of A. And I'll say something like maybe like together with negative absolute value B less than or equal to B, which is less than or equal to absolute value B, imply that important inequality that we use throughout each of the cases, right? Negative absolute value A plus absolute value B is less than or equal to A plus B, which is less than or equal to absolute value A plus the absolute value B. Okay. Maybe something like further note, because there was that other inequality that we used that actually, we don't need that other. We just need that information. That plus that gives us that, and this is the one that we use in both cases. Okay. So then we can say, we can explicitly tell the reader, case one. Okay. If A plus B is greater than or equal to 0, then the absolute value of A. Oh, I'm going to give this inequality a label. Call it A. You can do that, by the way. Write down an inequality and give it a label. So you can reference the inequality later in the book. So if this is a non-negative quantity, then by definition, this. That's by definition. Are all of you following me? I want to hear from each one of you. Are you following up to this step?
Yes.
Yes.
Right. It's 2.
Yeah.
It's okay if you're not, because I'll go back and I'll fix it, but just making sure that if that, then this by definition is equal to that. And that's the definition we have to write. Okay. Then combining this inequality A, which you gave it a label there, we have absolute value A plus B is equal to A plus B, which is less than or equal to that. Right, so see if that is less than or equal to that. So we're telling the reader by combining this with inequality A, we have, oh, case one has been satisfied. Then case two. If A plus B is strictly negative, or is less than 0, then the absolute value of A plus B is equal to the negative of the absolute value of the negative of the quantity. And this is again by definition. Okay? That's just a definition of the absolute value. Okay. So then what did we do? We multiply this inequality by -1, right? So then multiplying inequality A by -1, we observe, we have, or something like this, observe that the negative of A plus B is strictly less than the negative of this, which is just the normal quantity. Hence, the absolute value of A plus B, which is equal to the negative of A plus B, is less than or equal to that. In both cases, there's only two cases, it's either greater than or equal to 0 or less than 0. In both cases, we have established the inequality. So maybe you could just say in that out, the same in both cases. The absolute value of A plus B is less than or equal to the absolute value of A plus the absolute value of B. Got it. Okay. Now again, you're not used to working with inequalities, but you're going to get used to it. And you're going to use this triangle inequality quite a bit. In fact, I think I have one use case for it somewhere. But now that I've explained it, at least, after me explaining it, do you believe that it's true? Do you understand the logic that happens? Let me know. I'm waiting.
It makes sense. It's just the whole proving with inequalities thing that's still like settling in, I guess.
Right, and that's going to be there's going to be a learning curve there, right? Because we're looking at positive or negative, we're multiplying inequalities by negative numbers, we're adding inequalities. This is going to cause some pain a little bit. Okay. So this is the proof of the triangle inequality. So let's look at a technique that is used so much in real analysis. First, let me just restate the theorem. Triangle inequality. And again, just if A and B are real numbers, then the absolute value of the sum is at most the sum of the absolute value. Okay, so what was the thing? What did I have? Oh, so there's a corollary. A corollary is simply a result that follows from a main theorem, right? So this is going to follow from this theorem. It says that if A and B are real numbers, then the absolute value of A minus the absolute value of B is at most the absolute value of A minus B. Okay. Let me write that down right. Let me make sure. Yeah. Yeah, I did it. Okay. Actually, I'm not going to write down the proof first. I'm going to do exactly what I did prior. I'm just going to mess around with inequalities until I can see how to string this together. Now, the first technique that I'm going to show you happens all the time in analysis, and you just have to get used to it. All right, so I see absolute value of A. So what I'm going to do is I'm going to add a fancy version of 0. Those equal, right? Those are the same thing. Minus B plus B is just 0, right? So A plus 0 is the same thing as A. Do we agree? Let me know if you believe that this is equal to that.
What was the question?
Do you believe this is equal to this?
Yes.
Right, because minus b plus b is just zero.
Cancel each other.
Yeah, right?
Oh.
So I'm going to look at it like this, and then by the triangle inequality, we say that this is less than or equal to the first thing plus the absolute value of the second. Right? This is by the triangle inequality. Okay, do you believe me that this is less than or equal to that?
Yes.
Okay, because we proved it, right? The absolute value of the sum is at most the sum of the absolute values. This is the sum. Absolute value of the sum is at most the sum of the absolute values. Does anyone see how to finish off the proof now? You would put a smile on my face if you did. Just look at what we want to show, right?
Would we subtract the absolute value of b and move it to the other side with the absolute value of a?
Let's see what happens. Subtract the absolute value of b on both sides. Right? That. That was a good idea. Because now it looks much more like that, right? Well, if this is true, right, then surely this implies the absolute value of this quantity is at most the absolute value of this quantity. But this is already positive no matter what, right? So this is just the same thing. So that is at most that. You see that?
Yes.
All right. So that's it. So really, we can just say, yeah. So I think this is also, yeah, no, we just do it like that. So proof. So notice the absolute value of A, which is equal to the absolute value of A minus B, plus B is at most the absolute value of A minus B plus the absolute value of B. And the absolute value of A minus the absolute value of B is at most the absolute value of A minus B. Okay, so then you just take the absolute value on both sides, and then you're done. Oh, I almost forgot to say, important. Right there before that period, by the triangle inequality. Okay, important to put that up there before the period. Okay. Okay. So then another version of this is another corollary is that this is at most that. Okay. Okay. Sorry. Oh, wait a minute. What am I talking about? I apologize. Um, we didn't quite finish it. And I was thinking, I kept on pausing when I was looking at it because I knew something was off. So let me just write this again. So let A be your numbers. Okay. And observe that the absolute value of A, which is equal to the absolute value of A minus B plus the absolute value of B is less than or equal to this quantity by the triangle inequality. Yeah, you can't simply take the absolute value on both sides of the inequality. So hence absolute value of A minus the absolute value of B is at most the absolute value of A minus B. Okay, so next observe. So you just do the same trick with B now. Absolute value of B is equal to the absolute value of B minus A plus A, which is less than or equal to the absolute value of B minus A. Where is it? Plus the absolute value of A. Again, by triangle inequality. And you're doing the same trick again. Okay. So then, what do we have? Oh, we have hence. Again, what we're trying to look at is A minus B, right? So hence, the absolute value, the negative absolute value of B minus A is less than or equal to the absolute value of A minus the absolute value of B. All I did was subtract B on both sides and then subtract that on both sides. So what are the two inequalities that we have? We have this. We have this. Right? So how does that help us? Well, what it says is what? So what do we know? We know So maybe like therefore. We know that negative of this is less than or equal to this, which is less than or equal to that. Okay. So this looks a lot like, I should use the other marker. There. This looks a lot like the absolute value of the absolute value of this quantity, right? You see that? It looks a lot like it. It turns out, and I was missing this part from earlier, that this implies it's actually if and only if. And we'll learn why this is true, this if and only if next time. Why is this if and only if that? Okay. So I know it looks a little odd right now, but again, we're just adding, subtracting inequalities, multiplying inequalities by negative numbers, and that's about it. Okay. Let me see what else I wanted to cover. Oh, I should have mentioned this, that this right here, that's equal to negative of A minus B. Doesn't matter the order. So again, this is so one way of thinking about absolute values of distances is distance. So this is like the distance from B to A, which is the same thing as the distance from A to B. So maybe in your notes, and we'll cover this again, so the absolute value of the difference is the distance from A to B, which is the same as the distance from B to A. And it turns out that, so that less than or equal to that, which is less than or equal to the positive of it, holds if and only if the absolute value of this is at most. And again, we'll cover this next time, the simpler version of that. But again, today I just wanted to introduce you to what is coming, right? Sort of like how at the beginning of the semester, I showed you the square root of 2 being irrational way before you knew how to prove that. And then we built our way up to that type of proof. Same thing. Today, I'm showing you proofs that seem foreign and new, but we're going to build our way up there to those, being able to do this over the next 2 weeks. And we're not going to get into too hairy of proofs. We're going to just touch on real analysis so that when you show up to your real analysis course, that you're not like completely blindsided by everything. Okay, so I wanted to share with you my screen. So the textbook that I'm going to be using for the real analysis portion of this class is an Introduction to Real Analysis by Bartle and Sherbert. And this is also the real analysis textbook used by UH Downtown for Intro to Real Analysis. So if you're taking this course next semester, you might as well buy it, even though you can find a copy online, just like I found a copy online. This is the 4th edition. Okay. So, and I'll put this name up on Blackboard so that you can search it and find it. And then you can start reading through the first few chapters, and that's what we're going to cover. We're going to kind of skim through the first few chapters. Not really going super in depth, but we are going to cover the topics. Okay, so that will be it for today. I know it's been a rough one, but trust me, it's just the first day. Just introducing these techniques. There's still a lot more, but we'll get to them. And I'm sure all of you will be fine. All right. Well, stay safe, and I will see everyone on Thursday.